Nowadays, we are facing an increasing number of machine learning applications in modern data management. For example, a number of works have demonstrated how it is possible to improve the performance of query optimization by introducing machine learning-based algorithms. However, researchers have to satisfy some requirements to successfully apply machine learning to their pipelines in terms of quantity and quality of training data. Indeed, a proper amount of heterogeneous data is necessary to allow a machine learning model to learn even the most complex patterns. But it is not enough. Also, the feature engineering process has to extract sets of meaningful and high-quality characteristics from the data. And finally, supervised machine learning requires labels that, in case of data management, can be the execution times or the output cardinalities of the jobs. Sadly, the current data management state-of-the-art is more focused on developing new machine learning algorithms, assuming the availability of training data from the end users. And very few works talk about the elephant in the room. Collecting training data for machine learning-based data management is a real and complex problem. Indeed, to generate training data for data management, one has to manually create thousands of different jobs, and then execute them all to collect labels and to extract features. And as you can imagine, this can be a very tedious task. So, following the current practice of manually collecting labels, you may end up by executing thousands of jobs with very large workloads, and this can require days or even months. We extrapolated that this manual process can take more than 6 months if executing 10,000 jobs on 1 terabyte data. Surprisingly, the database community has made little progress in tackling the problem of generating labeled workloads. Very few and limited attempts have been made. For instance, TDGen, the previous state-of-the-art, proposes a synthetic generator of training data that is based on heuristics. It approximates the labels for the jobs through a polynomial forecasting, and it does not provide any warranties of producing a representative workload for the user use case. However, developing an efficient and reliable training data generation framework is challenging for many reasons. How we can generate jobs that are representative of an existing small workload? How we can take into account the real distribution of the data while generating a new labeled query workload? How can we efficiently produce reliable labels taking into account the performance of computing resources? And which is the smallest set of representative queries that should be actually executed to learn information that provides reliable labels? To face these challenges, we propose DataFarm, a novel framework that enables a data-driven process, learning from the execution patterns of an existing small query workload, from the user's input data, and from the user's computational resources. And furthermore, DataFarm is white box, meaning that it is easy to customize and debug it in every aspect, even in the machine learning steps. This is a very important feature, since if the user does not trust the process, he will not use it. This is the DataFarm framework. It is divided in 3 main components: the abstract plan generator, the synthetic job instantiator, and the label forecaster. The abstract plan generator analyzes the user's real workload and produces abstract plans. Then, the abstract plans are exploited by the synthetic job instantiator to create an augmented set of executable jobs. Finally, the label forecaster samples and executes a meaningful set of generated jobs, exploiting the user computational resources. This allows to initialize the active learning process that will allow to forecast the labels for the generated jobs in an efficient way. The final output of the process is the set of augmented jobs and their forecasted labels along with uncertainty values. Let's see now the details of each main component. The abstract plan generator learns the execution patterns from a small real workload provided by the user, and it generates new plans that are representative of the real ones. The abstract plan generator algorithm is composed of two main phases, the learning and the generation phase. The abstract plan generator learns the input plans patterns by analyzing them as Markov chains, and it represents them through two transition matrices. The children transition matrix contains the probability mass function of each operator at step t, describing its probability of transiting to any other child operator at step t plus 1. On the contrary, the parent transition matrix contains the probability mass function of each operator at step t, describing its probability of transiting to any other parent operator at step t minus 1. Then, in the generation phase, the abstract plan generator creates new abstract plans by starting from a data source and sampling the next operator accordingly to the children transition matrix. The generation process continues forward until it reaches a data sync or a join operator. In case a join is generated, the generation process starts a backward branch, sampling the parent transition matrices. Then, the process ends once the data sync operator is sampled or the user-defined max depth is reached. This is an example of abstract plan. Of course, it cannot be executed yet, since it is not a concrete job, but just an abstract representation of its execution flow. For example, the user-defined functions, such as selection predicates, have not been instantiated. The synthetic job instantiator creates an augmented set of executable jobs for each abstract plan, and it allows to include real input data, metadata, and custom user-defined functions in the instantiation process. The result of this step is an augmented set of executable jobs. Furthermore, during the instantiation process, DataFarm records all the decisions made by the synthetic job instantiator to be used in the next steps. DataFarm provides two interfaces to manage the user input data and the user-defined function. The Database Manager is the interface that allows users to include a new database with its tables and their relations. The Table Manager is the interface that allows to include per-table statistical metadata, such as table cardinality, the discrete distribution of each filterable field, and the number of distinct values in each group by field. So, given an abstract plan in input, the synthetic job instantiator recursively instantiates multiple job instances by exploiting the Database Manager and the Table Managers to populate each abstract operator with real user-defined functions. Also, this process guarantees the correctness of each generated job. Finally, once the jobs are instantiated, the label forecaster characterizes the jobs by means of interpretable and representative features. Then it finds the smallest possible set of representative jobs to execute, and it predicts the labels along with uncertainty for the non-executed ones. Also, the label forecaster implements an active learning process based on quantile regression forests. This is an iterative learning strategy that allows the label forecaster to reach high predictive performance with fewer training labels with respect to traditional machine learning approaches. The feature extraction process computes operator-level statistics for each generated job to efficiently and precisely characterize them, and enabling a high level of interpretability. Then, the active learning process starts. The jobs execution sampler selects the initial subset of workload to execute, exploiting an unsupervised analysis of the features that maximizes the differences between the available jobs. So, the selected jobs are submitted to the user's computing resources, and their execution times are collected. The model builder exploits the collected labels and the features to build a predictive model. Then, the forecaster exploits the trained model to predict the labels for the non-executed jobs. Finally, the uncertainty evaluator computes the uncertainty for each predicted label, and it decides if it is necessary to proceed with another iteration, which will execute more jobs to increase the accuracy of the model, or if the uncertainty is low enough and thus the learning process can stop. The final output of the whole process is the set of forecasted labels along with their uncertainties that are associated to the non-executed job instances. Let's discuss now the experimental results that we obtained thanks to Datafire. We generated a first synthetic workload composed by 2000 jobs, starting from just 6 TPC-H queries and 4 different scale factors of the TPC-H dataset. Here, we show the distribution of some meaningful characteristics of the operators composing the generated workload. Datafarm correctly distributes the available data sources among the generated jobs. This means that all the input data is equally represented. Also, the distribution of the other operators reflects the distribution of the input data and jobs. In this case, we can notice that the most frequent selectivity in the filter operators, in 39% of the generated jobs, is between 0.4 and 0.5, while just 9% of the jobs shows a selectivity between 0.1 and 0.2, and this is in line with the characteristics of the user input data. Instead, the complexity of the map operators is equally distributed among the generated jobs, while the number of joins per job follow the same distribution of the original input workload. The second generated dataset is composed of 1000 synthetic jobs. This time, we exploited the same small input workload already used for W1, such as the TPC-H jobs, along with the real IMDb database. This experiment demonstrates that with Datafire, we can extend any input workload to any input data. Thanks to the active learning approach, our framework predicts the labels by executing only a few jobs from the generated query workload. The task in this case is to label the non-executed jobs by predicting their execution times, exploiting the active learning approach implemented in Datafire. To measure the quality of the forecasted labels for the non-executed jobs, we computed the R-squared score among the ground truth values collected executing all the jobs manually and the values predicted by Datafire. Also, you can notice that each predicted label is associated with its uncertainty range. These uncertainty values help the user in better understanding the performance of the predictive model and to decide if to continue with the learning process. In our experiment, by executing just 142 jobs for W1 and 418 jobs for W2, Datafarm achieves very good R-squared scores, meaning that the model has properly learned the performance trend of the synthetic jobs. So, for example, in the case of W1, we avoided the execution of more than 1,100 jobs, saving a considerable amount of time and reaching a very good accuracy in terms of predicted values for the non-executed jobs. Here we compare against the old state-of-the-art, known as TDGen. These plots show the accuracy in predicting the labels for the non-executed jobs as function of the number of executed jobs exploiting our framework and TDGen. We demonstrate that, in comparison with the previous state-of-the-art, our system is up to 6 times more efficient, requiring to execute much fewer jobs, saving a considerable amount of time. And it is also 9 times more accurate in predicting the labels for the non-executed jobs. Now, we want to demonstrate the effectiveness of a dataset generated with DataFarm in training a machine learning-based data management component. To do so, we train a machine learning-based component to predict the execution time of jobs, exploiting W1. We used first the ground truth values of W1 jobs, and then we used the labels produced by DataFarm. Then, we used the model to predict the execution time of an input workload. In the plot, we can see the gray line representing the real execution time for the input workload. Instead, the stars are the prediction made by the model trained on ground truth, while the red dots are the prediction made by the model trained with DataFarm labels. From this result, it is clear that DataFarm produces high-quality labels, comparable to the ground truth, in a much more efficient way. Indeed, the performance of the machine learning-based component are reduced of just 1% when using DataFarm's labels with respect to ground truth. That is a totally acceptable result if we consider the other advantages that DataFarm can bring to the user. In our experiments, DataFarm significantly improves the performance with respect to manually collecting labels. There are 2 factors that can affect the time required to collect the labels: the size of the input data and the number of the generated jobs. We measured that, increasing the size of the input data up to 50 GB and the number of generated jobs to 2,500, DataFarm improves the performance of labeling the jobs, respectively of 3.4 and 16 times. So, combining the 2 results, the total improvement factor will be more than 50 times. Also, we extrapolated that if increasing the input data to 1 TB and the number of jobs increased to 10,000, the improvement factor will improve even more, reaching 2 orders of magnitude. In conclusion, DataFarm is an effective and efficient framework for generating training data for machine learning-based data management that takes into account the user input data and already existing workload. Furthermore, it provides accurate labels to the generated jobs, executing only a small amount of them and taking into account the user's computational resources. Also, DataFarm outperforms the current state-of-the-art, being 6 times more efficient and 9 times more accurate. Moreover, one can achieve 2 orders of improvement factor with respect to manual labeling. And DataFarm can be easily extended to support any data management platform and other kind of target label generation, like, for example, output cardinality.